Hi, everyone. I'm Doug Edline, and I'm going to talk about Julia language today. And really, it begins with what's after Python. And the title of this little talk is Beyond Python, Julia and the New Path Forward for HPC and Technical Computing. And we all use Python. It's great. And when we get to technical computing, it tends to get stretched a little bit. And for that reason, I want to talk about Julia and the new path forward for HPC and technical computing. My goal here is to give you a taste of what Julia is about. We're not going to become experts in the time we have this morning. And just to give you an idea of what topics Julia addresses and some of the features that you can look forward to if Julia fits for what you're trying to do. A little bit about me. You can contact me at any of those email addresses there. I'm also on Mastodon and Twitter, if that's your kind of thing. And currently, I'm the managing editor at hpcwire.com. And if you haven't been to the site, please visit. We like to cover the fastest computers in the world and the people who run them. We're really the go-to site for HPC information. And we've been doing it since 1987. So I'd love to see you land on the site at some point. So from a background standpoint, I've used different languages and I've used Julia, and I find it to be a very remarkable and useful language for doing technical computing. And before we get into Julia, I want to talk about a few things. One of them is the resources today are available at this URL, www.clustermonkey.net/download/Julia And in there, you'll find a zip file and a tar gzip file, which will include some of the code I'll talk about today, and also PDF version of these slides if you want to review them as well. So the question is, why Julia? I already know Python. And there's an important topic we have to talk about that happens particularly in high performance computing and technical computing. So it's the two language problem in HPC. You know, how it started. I need some code for my research. I start hacking together some Python. There's all these great libraries. It seems to work pretty well. And now I'm like a coding hero. I've got this tool that maybe I share it with some of my research associates. I put it on GitHub, share it around. Everything's great. And then I start adding features and find out it gets slower. And then I think, well, you know, maybe if we could have it use a GPU, some of the matrices are getting bigger and so forth. And we want to be able to add more data. And then eventually what happens is you get to the point, well, you know, I really should rewrite this in an HPC language. Now, I have that in quotes because that can be a lot of different things. Traditionally, I'm going to rewrite it in C, C++ with MPI. Or, you know, I'm a real traditionalist. I'm just going to use Fortran and MPI. And I rewrite it. It does a lot of the same things, only now it's scalable. I can have more data. I can add bigger matrices, bigger features, for example. The problem is now I have two versions. I've got one that runs on my laptop that I've, you know, may add a feature or two. Then I've got another one that needs an HPC cluster and probably runs maybe in using C or C++. And I could try maybe getting a Python version to run on the cluster with MPI, but that starts getting a little messy because it wasn't really designed for that. So this is the situation that oftentimes develops, which I have over-exaggerated with this picture here. So But this is this is a lot of times what happens. You get started easier, nice and easy, and then you run into an issue with getting things to scale and running at scale. And then, so I list down here some of the computing languages that are available. There's more than this, obviously. Fortran, C++, Java, Python, R, Spark. There's a bunch of others. And then you have to start thinking, what language do I want to use if I'm not going to use Python? Well, back when the Julia team from MIT first got started, they published this manifesto, which I think was really bold at the time. And it's something this, as a user programmer, this is what I wanted. So they said they want a language that's open source with liberal license, so anybody can use it. They want the speed of C with the dynamism of Ruby, meaning it's can be dynamically, things can happen dynamically. They want a language that's homo-iconic. That means it can also process its own code, treat its own code as data with macros like are found in Lisp, but familiar mathematical notation like MATLAB. They said we want something as usable as Python. So they know all about Python. Easy for statistics as R, as natural as string processing as Perl, as powerful for linear algebra as MATLAB, and good at gluing together programs as the shell programming does. Something that is dirt simple to learn yet keeps the most serious hackers happy. They want it interactive, and they want it compiled. And this was a pretty tall order at the time. And I thought when they first started it, I thought if they're successful, this is going to be a pretty powerful language, because they, rather than worrying about some of the fancy features of the language, they were actually looking at what people need. And I think all these things listed in here are what a lot of people need. And the thing I like is dirt simple to learn. That was a key thing. So a little bit of the official history. In 2009 is when they started working on it. Viral Shah, Jeff Bezanson, Steve Kruponsky, and Alan Elderman, all of MIT. They started this. Originally, it was MIT and GPL2 license, so it's open source. It was officially released in 2018, and each year they have a JuliaCon. And it's reportedly doubling its user base every 9 months. They established a company called Julia Computing in 2015 to provide paid support, training, and consulting to clients. It does not impact the open source nature of Julia. There's no like pro version. It's pure Julia that's downloaded. And you can basically buy support for it if you want, and training. So what I thought initially, well, does Julia succeed on ease of use? And having seen a lot of different programming languages, I said, well, let's take a look at a little piece of it. And this is just a function, Mandelbrot function. I don't care what it actually does specifically, but I can look at this and pretty much figure out what it's doing. There's a for loop, there's an if statement, a return, another return statement, there's a function declaration, variable assignments. So it looks pretty easy to follow, pretty easy to understand. Obviously, it can get a bit more complicated, but first blush, it's fairly easy. Now, what about performance? So some of these benchmarks are a little bit old, and the trend is still there. So what they've done is they had this really hard to read chart but everything's normalized against C. So every program is normalized to essentially as fast as a C as it would run in C. And then these are the differences for these types of programs listed on the right. How much different they are from basically running as C. And you can see some of them are lower down the bottom, meaning they run faster than C. And they did this for a bunch of different languages, Lua, Rust, Go, Fortran, Java, a whole bunch of them. And you can see the disparity that tends to happen here, where Julia is pretty tight, so is Lua. And as you get further to the right, where things get a little bit actually easier to use, so starting with MATLAB and Mathematica, Python, R, Octave, you can see the performance really starts to drop, or gets time to completion gets longer. So you can see that Julia really is, if it keeps that ease of use bit, it's really got something going in terms of performance, because it's up here with these other languages that do really well. Now, to kind of give you some numbers on this. So here's the graph, and this is old, and these trends are still the same. So you have things like Fortran and running these. Here's the programs they're running, and this is normalized to see how much faster or slower they are. So in this case, Fortran's 0.7 is faster than C, and you can see it does very well. Here's Julia version 4.4. That does pretty well too. But when you get up to things like Octave, which are very easy to use, by the way, and I don't know if any of you have used it, or things like MATLAB, there's some real disparities in terms of performance. And this was one of the things that Julia was worked on from day one. Was they wanted performance out of an easy to use language, and I included some others. And again, you can see things like Go and Lua do very well. Mathematica, not, as we saw, not so well in some cases. And again, it's about ease of use. So most people who've used Python or MATLAB can pick up Julia really easy, where if you're learning something like Go or Lua, it might not be as easy a stretch to get to learn a new language. And that's one of the goals, ease of use and speed. So a little drill down on the what I just said, that many technical computing users start with easy tools like MATLAB, GNU, Octave, R, Python, Mathematica. And I want to point out that's a very reasonable choice. It makes perfect sense. It's there's no fault in picking one of these, ease of use to get something up and running. And then pushed further into the technical computing space, they tend to face limitations in terms of speed, expressibility, and I call that abstraction in terms of maybe you want to express something that runs in parallel across a cluster. They don't have a mechanism to do that within the language. And then basically end up forcing applications to write in a performant language. In other words, have to write something in a more performant-based language that maybe has different libraries that aren't available in the other language, or are certain and different features that may be needed. And like I said, the classic thing is usually using MPI and some other language. So, and that in itself represents a very big leap in terms of programming. MPI programming, while isn't impossible, if you're not a seasoned programmer, can really be an impediment to getting things working on a cluster, say. And that's why, a lot of the data programming, data science, big data languages like Spark are designed to scale pretty much transparently, but they're not the same. They don't provide the same type of features that are needed in technical computing. So the idea is Julia provides an easy starting point. So all the other options up there are still good, and Julia is just as well. And it allows your application to grow into the technical computing space. So you get the best of both worlds. And one of the little things they like to talk about is it walks like Python, runs like C. So that's kind of one of the taglines for Julia, and it's why people like it. I always like to see, well, who's actually using it? Or is this an academic language, or is it, something that actually get used? And this was an early 2015, the Federal Reserve Board of New York, they actually started using Julia for some macroeconomic models. We don't need to know what they are. Very complicated. And, I always find it interesting when, something that has to do in the financial markets, when they take up a technology, that to me is usually a bellwether of, how well something may be adapted later on and will grow, because they're usually very conservative and they don't use new things lightly. And when asked why they did this, they cited speed and cost. And there's the case is there. There's a URL to find it. So they saw right away the value of Julia. And so it's one of those cases where this wasn't just somebody in a lab running their example program with Julia and saying it runs faster. This was actually in a production system where they had to run models and publish results and so forth. So that was a quick overview of some background, the ease of use features. And again, if any questions come up, put them in the Q&A box, and I'll get to them as soon as when we switch over to actually take a look at some code. That way I can, because I can't see the Q&A box right now. So while I'm screen sharing this, so we'll any questions that come up, we'll take a look at that. What I wanted to do now, very quickly, was go through some of the standout features of Julia. And this next slide is a little bit busy. And I could probably do like 3 more slides, but basically these are the ones I find most useful. Some of these I already mentioned: simple syntax, similar to MATLAB. It's a high performance LLVM based compiled and just-in-time compiled. There is a compiler now, and there's just-in-time compilation when you're working interactively. It really does match the performance of C and C++ in many cases. It's a typeless language with this weird thing called multiple dispatch, and I'll talk about that in a little bit. That's something very new to many languages. It can be emulated in other languages, but multiple dispatch is something that's native to Julia. It's got plenty of growing packages and libraries. Every week I usually see a new one show up. It can call, this is what I really like, it can call Fortran and C functions directly without wrappers or special APIs. So if I have a Fortran library that has written something that's very useful, I can call that directly from Julia. It's designed for parallelism and distributed computing. That includes multi-core and clusters. So that's built into the language. There's no need for MPI. It's got a lot of capabilities to manage processes and do things in parallel. It's got powerful shell-like capabilities for managing other processes. So you can do some things in it like you can normally do with shell programming. It also has its own notebook, like a Jupyter Python notebook. It's called iJulia. It's got plotting, graphics, GPU access, and I'll mention some of that about that in a little bit. Pretty much all you would expect, a lot of the things you find in Python, except, Python can certainly boast a huge amount of libraries and additional functions that are coming to Julia, but it just, Python had such a huge start. And it also has, when it added math libraries, it didn't rewrite them. It usually used the best of breed C and Fortran libraries for things like linear algebra, FFTs, and so forth. So that's a lot of the nice features. I want to just give slight examples, and the programming tools I'll mention will illustrate some of this. So it's typeless, a typeless language. In other words, you don't have to specify the type. You can of a variable, but you can do things like multiply a decimal number times an integer, and it knows enough to report it as a decimal number. Or you can do things like assign a string, and it will assign a string to the variable. So you don't, the variable doesn't have to be declared. The type of the variable can happen at any time you want. Now this multiple dispatch bit. So this is what's interesting. We can easily define a function called combine, and we can call it with two strings, combine 1, combine 2, and what it's going to do is return one string with both strings. And that makes sense. At the same time, however, we can call combine with 1, 2, two integers, and it's going to add the integers together. So that's a bit different than concatenating strings. We're just adding them together. And then if I said, I'm going to be tricky, I'm going to say, okay, combine 1 and this integer 1 and the string 2, it's going to say I can't do that. Now, this combine function, and I actually give an example in the code, is easy to put together, where you can tell Julia, based on the arguments, the types of the arguments, you can direct Julia to do different things. That's what multiple dispatch is, that you can have the same function name, and depending upon the arguments, you can direct it to do different operations. In this case, concat 2 strings. In this case, add 2 integers. And in this case, say, I don't know how to do this because you want me to combine an integer and a string. So multiple dispatch is useful because you can have, instead of having a bunch of different combine underscore string, combine underscore integers, different types of combine functions, you can have one function that is defined by the arguments. And this can be very useful when you're abstracting away things like hardware, GPUs, and things that you can very easily just have the same function with different arguments, different type arguments, and it will direct it around in terms of what to do. So, and like I said, in the code, I have a little example of that. The other thing that I mentioned, functions can be called directly from Julia. So I can, it's different for Mac and Windows and Linux, but I can assign using a call to the C library, libc, to the clock function, and it will turn the number of seconds. I think since January 1, 1970. And it does it. The library's different in Linux, so it's called that. So you can interface with these libraries. They're already written without doing anything different, having to write a wrapper or anything like that. Can be very useful. What about parallel and distributed computing? Well, here's a very simple example. And again, you don't have to really know exactly what happens, just that I'm going to start Julia. That's what, when I type Julia, the -Q means quiet. And I'm going to tell it to add 3 cores, 3 more cores to the current running Julia. So when I run programs, it's going to use 4 cores, essentially. So I start Julia, I type use distributed, using distributed, which is the library. I tell it nprox, how many processors do I have? It says 4 because I started it with a -P3, which is add 3 more cores, not use total of 3. And then I just do this simple thing where it's going to run simulated coin flip. It's just going to add up all the ones. It's going to do a random 0 or 1, add up all the ones, and that's how many, we'll just call it heads, it comes up with for, what's this look like, 200 million times. And we get 100 million almost heads, and we notice it's not exact, which makes sense because it's random. So it will do that across 4 processors. So you can do other things. There's other way to manage processes and move data and so forth. I won't dip in too deeply. But that's one of the things that it's made it easy to run things across multiple cores, which you can do on a notebook and you can do in a cluster. So it's actually fairly easy to translate from one to the other. And you can easily, instead of using multiple cores, you can use multiple servers, and it'll transfer the work, the job over to another server. You can run shell scripts within Julia. So the uptime, which says how long whatever's been running, I can just run that command and it'll print it out. I can capture that output into the variable A and get the message of the day if you just want some text. And so then it will store this into that A variable, and I can do things with it. I could also run store uptime and get the uptime data if I wanted to. So it just shows you the flexibility that Julia provides to do things that we all mostly like to do. Another thing, iJulia notebooks. Here's an example here. So that's available, and you pretty much have everything you're looking for. It can do all kinds of graphics with Gadfly that you want to do, and there's more options now. This slide's a little bit old. So there's lots of things you can do that you can do in Python that you can do with Julia, and you're setting yourself up for growth is one way to look at it. It also includes, as I mentioned, the best of breed C and Fortran libraries, because it's so easy to add these libraries. Why rewrite them? Just bring in things like LAPACK, OpenBLAS, FFTW, all those things where a lot of work has been put into optimizing these codes. Well, we can just dump them directly into Julia with little work, and actually they're available abstracted into Julia. You don't even have to worry about adding them or anything like that, just adding a library. Things like GNU multiple precision arithmetic library. If you're doing something and you need really high precision, big int numbers, you can do that. So So I often, when I present this kind of stuff, I get, yeah, but what about R and Python? I use those. They're great. And yes, they are. They're good languages. And I think when I draw my list of things that are important to me, modern features, speed, data handling libraries, parallel distributed, and technical computing, and I sum these up, what I find is Julia seems to win. Data handling is getting better. R is definitely much better at that. Libraries, that's getting better, but things like R and Python definitely win with the libraries because they've been around a lot more. But the speed wins are Julia, and modern features are definitely Julia. So that's why I'd like to, when I tally up my list, that's why Julia wins for me. So what we'll do, I just want to mention, if you go to julialang.org, that's the website, and you can click on downloads. There's releases for Windows, Mac OS, Mac with Apple Silicon, Linux, even FreeBSD versions available. So, and there's usually there's a little script you can download that will install everything. That's actually fairly easy to do. They make it very easy to install Julia for your platform, so much so that I won't even go into that aspect. So what I wanted to do, and given that we've got limited time, I wanted to just I'll just point one thing out, and then I'll leave it as homework. So I'm going to stop sharing. And I'm going to screen share a text window, and realizing that we don't have a lot of time, I'll just give you the skinny on this. So on the site that I gave you for downloading code, there are two packages. There's a Julia Del code with today's date, TGZ, which is a tar gzip package, or a zip package, exact same thing. If you extract those, you're going to get a directory called Julia Del. Now, I've got some other stuff mixed in here, but if you go to that directory, you'll see there's two subdirectories and some README. That's if you want to contact me. My email's in there if you forgot that. Julia basic examples. If we go into that directory and type ls, so we've got something called a notes file, and then a bunch of Julia programs. .jl means a Julia program. And if you open the notes file with your favorite text editor, these are just ASCII text notes. So in this case, I'm going to use VI. And it's basically some annotated commands and what things you can do with Julia. And it looks like this. It gives you running shell commands and examples, managing execution. You can work through this if you want, if you're curious about learning a little bit more about Julia. It goes on, covers quite a bit. Many of the things I did today. Now, once you've installed Julia, to start Julia, it's just simple as typing Julia. And of course, you get this not found because I did not update the bash script, and I wonder if there we go. I had to update the environment after I installed it. So you'll get something that looks like this. You'll get this ASCII art and some things. But basically, that's your Julia interface, just like you would have with something like Python. And you can enter a question mark, oops, and it'll switch to help. And here's the, whoops, print line function. Come on. Print line function, and it's going to give me help for print line, things like that, and flip back to this, the Julia prompt. So you can work through some of this stuff in the notes files. If you want to learn a little bit more about Julia and all kinds of fun things there. You can also, depending upon your environment, you can open these notes files in any kind of editor. This is on a Mac, so VI is included. You can use things like, I think I have Nano here. The Nano text processor makes it a little easier to use. It's got some help keys down the bottom there and so forth. But that's a whole other lesson. So there's the ability to try some things with Julia in these files. And there's also another directory called Julia Extra Topics, where I have some examples of extra topics as well. And these are all freely available to use and try and learn a little bit more about Julia. So once you get it installed, you can start using it. The other thing is you can also, there's some instructions online as to how to install the Julia notebook as well. So usually it's a little easier to start out with the command line. So what I want to do, in case some questions have come in, is look at the Q&A widget here.
Okay. Yeah, Doug, thanks. Yeah, I can help drive that Q&A.
Okay.
That way you don't have to like type any answers in or anything, but great presentation, great hands-on as well. Very informative. So looking at the Q&A, if you have put a question in there, go ahead and raise your hand. That will actually enable me to promote you to be able to ask your question. So first I'll go ahead and promote David Chin. David, I know there was also some discussion about your question in the chat, but let you go ahead and raise it for everyone and provide any additional context that you like as well. So I think he was on and then dropped. Hold on, let me see if I can promote him again. Oh, not there. Well, let's, Doug, maybe we can just go ahead and you can talk to this.
So Julia includes its own communication libraries. So it will, when you're moving data between processes, it will do that on its own. It doesn't use MPI. So it doesn't, I believe you could, if you want to do MPI programming, there is an MPI library for Julia, but in most cases for things you want to do, you could do it. It's got its own internal method for basically moving messages and moving data. And it will allow you to do, say, for instance, distributed computing, meaning you can take an array and break it up over certain number of cores or certain number of servers, and it will manage data between the two and allow you to do operations on, the different servers, and it just manages all that in the background.
Great. Okay. Thank you, Doug. I'll go ahead and promote Vinod Gupta next and share his question there. Vinod, you can unmute and provide any context around your question you like. Sometimes it takes a moment for the platform to unmute it. There we go.
Okay, thank you. I love a mission statement of Julia. That's easy and fast. I have a question about this ease. I think every language starts easy but ends complicated. What stops Julia not following the same path?
Yeah, so that's a good question, and I think there's two things that Julia brings to bear, and it's a much longer discussion. But the fact that multiple dispatch allows it to abstract some complication away from the end user. That means as you add features, it does not get more complicated. Obviously, like one of the things that's important today is using GPUs, and Julia has its own GPU matrix libraries that are basically abstracted. There is some dependency on hardware. Obviously, you can't really get away from that, but make it very easily to swap GPUs, AMD or NVIDIA within your program, and just use a different one without changing the whole program and the way things work. So that's one piece. The other thing is, what I found in general about Julia is the developers and now the users, the developers are more users, so they tend to make things work the way you would expect them to, and make them easy going forward. I've been really impressed in that every library that I've used makes a lot of sense, how it's constructed and how it works. And I think there's a real effort to keep that from happening, having it get more complicated. And I think the only true test of that will be in about 4 or 5 years, maybe, when some real big projects have been done in Julia, and some have already, by the way. And most people say they like the idea of the simplicity. So I don't have an exact example to provide for this case, but I found it to be well thought out from the beginning, with the idea of being able to grow without a lot of complication.
Great. Thank you, Doug. Thank you, Vinod, for the question. All right. Oops. Sorry. All right. I do not see any other questions in the Q&A at the moment. If anybody does have a question they want to raise, feel free to put it in, or go ahead and raise your hand and I can promote you as well. While we give that a moment, I guess, Doug, to see if anybody else has a last minute question. You have commented on the specialized libraries and stuff, if you will, but can you provide any additional context around the interoperability of existing HPC software stacks?
Yeah, well, if the libraries are written in basically C or Fortran, C++, you can very easily integrate them into Julia. It's like the example I showed, the simple one, calling the clock function from glibc or something. It's very easy to do, and they actually have integrated, as I mentioned, the best of breed already into Julia, and that's one of the things they wanted to do from the get-go, was make sure things could be integrated easily and not build their own little walled Julia garden. So all that capability is built in from the beginning. Also want to mention, I put in the chat that website that has the slides and the download, so you can go check that out if you want. And it's got the code download. You can pull down and extract and use with Julia.
Okay, great. Vinod put one additional question. I'll just share that here briefly. So are there tools for code migration from Python to Julia?
That I don't know. Good question. Language migration is a tricky thing. I suspect somebody might be looking at something like that, but that's a tricky thing to do and get right.
Okay. Let me check. Looks like we have another one. Let me share this. All right. So are there existing containers with Julia pre-installed? Also, are there good profiling tools?
The answer to that is yes and yes. So there is a Julia debugger, and there is it's very easy to profile different pieces of Julia or the whole program. So the profiling is actually, performance profiling is built in. And the debugger, which was missing for a while, is also available as well. And I'm sure there's containers with Julia. It's pretty easy to install. I generally use it native without containers. So I am going to have to drop soon because I do have a.
Yeah, I was just about to close early, but yeah, thank you, Doug. And for those of you who joined us today, we do appreciate your participation. And we were planning to end a couple minutes early here today so Doug can get to his next meeting today. But thank you again, Doug. We really appreciate your time and support and this information on Julia today. So thank you very much.
Yeah, and any questions, just my email's in there. Just send me an email. Love to help you out if you have any questions about Julia.
Great. Sounds good. Thank you. Have a good day, everyone. Bye.